So let's continue. So we talked about generalizing the notion of a Cartesian product to arbitrarily many sets, like we have a collection of sets. And we just observed that in order to define the product, whatever that would be, we need some kind of labels for each set. So let's introduce some definitions regarding that. Okay. Let J be a set. So this J is the set whose elements are supposed to be multiplied. Well, I shouldn't really say multiplied. Let's say whose product is to be taken. So you can forget it, you can ignore this parenthetical remark at the moment. I just have a set. The set would be the set which contains all the sets that I'm going to multiply, okay? J has its elements as sets. I want to define the Cartesian product of all these guys. Okay? But I need a labeling. Okay, stop writing. You should follow, then you can write. This is my J. These are its elements. I want to define the product of these guys. I want to label these. How can I label these? I can create a set of labels, and each label here will label some guy over here. How can I do this? How can I formalize this? I can do this by a function from I to j. Okay? So let I be a set, and this f from I to j be an arbitrary function. Now let's recap some definitions from last time. A function is simply a well-defined relation. But when I talk about a function from I to j, I also put some extra restrictions. Namely, the restriction that the domain of f is a subset of I, and the range of f is a subset of j, okay? Well, sorry, the domain of f is exactly I, and the domain of f is, sorry, the range of f is a subset of j, okay? Well, Mehmet is not here, but that would actually answer his question, which he asked last lecture. Anyway, we refer to f as an index system of sets, okay? With the index set I. Now, I have a set J. J has its elements. I want to take the Cartesian product of all these elements at the same time. I need labels for this. So I create another set I. This is the set of my labels. Now I consider a function from I to j. And that basically labels each set. The label of this set is this guy. The label of this set is this guy. So I just name every set in here. When I set a function from I to j, I don't simply mean this is like a well-defined relation. I have extra conditions. When I write this down, the domain of f is exactly I, and the range of f is a subset of j. Okay? So that's what you were talking about. Like a function from I to j means that there are no elements left in the domain, blah, blah, blah. Okay? So we're going to refer to this as an index system of sets, to this function, with the index set I. So this is the set of my labels, okay? Here we think of an element little I of I as a label for the set f of I. This little I is mapped to some guy in J. So it's just like this. Let's say that this is I. This is mapped to this guy, f of I. F of I is this set. I think of I as a label of this set, okay? Now, I just introduced some terminology, but I'm going to be somewhat flexible while using this. So sometimes I'll just refer to the image of this as an index system of sets and so on. So let me write those down. Okay. While talking about index system of sets, we sometimes write f sub I for f of I, and we use this notation for the range of I, and to which we also refer as index system of sets, as an indexed system of sets. Now, this last two sentences, they're just about terminology, okay? An index system of sets, it's a function. The domain of this function is the index set. It's the set of my labels. The range is the set which contains all the things which are going to be labeled by this function, okay? As I said, we think of I as a label for the set f of I. Now, it's customary to write f sub I when you talk about index system of sets. You probably have seen this notation, and you will keep seeing this in your future life. This is what notation people use for index system of sets, and they also use this notation, okay? Curly parentheses f sub I, curly parentheses I and I. So they mean when they write this, they mean the set of all f of I, namely the range of this function, okay? The image. Sometimes people also refer to this, just the image, as an index system of sets. Okay. So how are we going to define products? Definition. Let f from I to j be an index system of sets. So it's simply a function, okay? With the index set I, that's obvious. The product of the indexed system is, now I'm going to define the product of all these sets. I'm going to define the product of all these sets. How am I going to do that? This is A, this is B. How do you take the Cartesian, what's the Cartesian product? This is the set of all ordered pairs such that A comes from A and B comes from B, right? Say yes? Yes, okay. Now, let's do the following. Let me take the union of A and B. And over here, let me have only two elements. in order to represent the ordered pair AB, I can do the following, right? I mapped, let me name this 0 and let me name this 1, whatever they are. We will define natural numbers later. Let me look at the function which maps 0 to A and 1 to B. I can think of this function which maps 0 to A and 1 to B as this ordered pair. They're different objects, but I can make an identification, I can make an association, okay? I think of the function which takes this guy to this and this guy to this as this ordered pair. If 0 is mapped to some other guy, this function, I will think of that function representing, I will think of that function as representing this ordered pair. So in order to, when I have two sets, when I take the Cartesian products, I can look at ordered pairs. Now over here, I can't have infinitely many sets. So I can't really use ordered pairs. Ordered pairs are simply like they have two components. I somehow need many components, whatever many means. Now in order to get around that problem, what I'm going to do is this. I'm going to use functions. First of all, let me show you how we denote this. The product of this indexed system is shown by this. This is your index system, you take its product. This product is defined to be the set of functions, the set of all sets such that, the set of all sets such that, the set of all sets f such that f is a function from the index set to the union of J such that f of I belongs to f sub I for all I in I. So what have I done here? Again, we don't know what natural numbers are at the moment, but pretend that you know what natural numbers are. 0, 1, 2, 3, dot, dot, dot. And let's say that you have a set over here. Let's call this J. And this is an index system of sets. So each set in here is labeled by something. Let's say that this is labeled by A0, this is labeled by A1, this is labeled by A2, and so on. And this is labeled by A3. Now, an element of the product of this index system of sets is a function, according to this definition. It satisfies some special properties. First of all, it should be a function from I to the union of J. So I have a function which goes from here to, it doesn't go to J, it goes to the union of J. So I take the union of all these guys. Okay? It's a function from here to here. It's a function such that the value of this function at I belongs to the ith set. So it's a function such that f of 0 is an A0, f of 1 is an A1, f of 2 is an A2, f of 3 is an A3. So what I'm doing is this function, intuitively, this function for each I chooses an element from the ith set. This function chooses an element from the ith set. Okay? Now, how does this help? Take any such function. Okay. I want to take the product of all these sets, right? I want to define the product, and here's the definition. What I'm telling you, like, here's the definition. An element of the product is such a function. An element of the product is simply a function which chooses one element from each of these sets. When you have only two guys, it chooses one element from here, one element from there. It's just like the usual Cartesian product, except we don't use ordered pairs, we use functions. And this like when you use functions, this can be generalized to arbitrary index sets and arbitrary sets. This is the product, this is the Cartesian product of an arbitrary index system of sets, okay? It's the set of all functions satisfying this property. Is this understood? Now, let me show you why this is useful by introducing another notion. In calculus, you learned about sequences, right? Everyone knows what a sequence is? No? So you don't know sequences. How did you pass 154? You know about sequences, right? Sequence of real numbers. Here's the question, what's the sequence? What's the sequence of real numbers? Let me write down a sequence of real numbers. 2, 1, 1/2, 1/4. What's the sequence of real numbers? It's just a bunch of symbols. But what is it?
Set of numbers.
It's a set, yes. But what is it? I'm not expecting an answer because until now you probably were not told what's the sequence with index set natural numbers over the real numbers. Here's why this is useful. Here's how we formalize all these. I can think of this sequence as a special function, as a special kind of function. It's a special kind of function from natural numbers to real numbers. It takes 0 to 2, 1 to 1/2, 2 to 1/4. So label of this guy is 0, label of this guy is 1, label of this guy is 2, label of this guy is 3, and so on. So I can think of the sequence as a special kind of function. Is this understood? What am I doing over here? These are my natural numbers. This is my J. The elements of J are simply, it's the same set, it's just real numbers. There's only one set in here. Okay? So the union of J is real numbers. A function from this index set to the union of J satisfying this property, f of I belongs to the ith set, is simply a function from natural numbers to real numbers. Okay? So if I ask you what's the set of all sequences with index set natural numbers whose entries are real numbers, it's the set of all functions from here to here. Right? And I can construct it like this by doing the following. I choose my index set to be natural numbers. I choose my J to be the set containing real numbers, whatever this is. And I'm saying the following. F sub I, the ith set, is always real numbers. In this case, this would be simply real numbers, this would be natural numbers. I would have the set of all functions from natural numbers to real numbers, which is the set of all sequences. And this is how we define sequences. Okay? Like this sequence is indexed by natural numbers. Have you ever seen a sequence indexed by real numbers? The length of your sequence is like real numbers, whatever that is. But we can talk about such sequences using this notion. Okay? I really shouldn't have said length of the sequence, but the index set. Anyway, so definition. Let S be a set and I be an index set. then a sequence, an element of the product of the indexed system S sub I in I, S sub I equals this fixed set S. So my function f here is simply the constant function. All the elements in the index set is mapped to the same thing. They're mapped to a single set S. If you look at this product, you'll see that this definition reduces to the following. I have functions. These functions are from I to the union of j. And I choose my j to be simply this set, the singleton containing S. So the union of j will be, in that case, S. So this product will be the set of all functions from I to S. Okay? Questions? So a sequence, when someone talks about, oh, I haven't finished the sentence, no one's warning me, I need to finish the sentence. An element of the product, blah, 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 of the index sets is called a sequence over S with the index set R. Sorry, I, not R. So when someone talks about a sequence over S with the index set I, he or she talks about a function from I to S. And we think of these functions as representing sequences where the entries of my sequence are elements of S, and the entries are labeled by I, okay? So a function from real numbers to real numbers can be thought as a sequence of real numbers where the index set is simply R, okay? So for each real number, you have a real number. So you're basically, this is like, think of this as a sequence, except your index set is something that does not allow you to write this on board in order, okay? Now, we define these, and these guys exist. Like, you can prove that all these guys exist by using the axioms we've introduced so far. You don't need anything else besides the axioms we've introduced so far. But here's the question. This exists, but so does the empty set. And my question to you is, why is this not empty? How can I find such a function? Now, this question is actually really important. But before that, I'm going to give you two exercises. Otherwise, I'm going to forget about assigning these. Let me write down two exercises over there, and then we'll talk about the axiom of choice. The first exercise is this. Okay. Again, you don't know what natural numbers are at the moment, but I'm giving you the first three ones. So 0 is the empty set, 1 is the set containing 0, and 2 is the set containing 0 and 1. Okay? You're given this. Let AI, where I change this in 2, be an index system of sets. Now, this is something new. I don't think that in any other class you've seen this. Something belonging to a number. Well, in this course, anything can happen, as long as it's not a contradiction. 2 is the set. I have an index system of sets. So this is a function from this set. This is a set. Yeah, it's a function from this set to some set, and its elements are like now A0 and A1. It has 2 elements. It may have more elements, but yeah, I didn't put that restriction, but I don't need it. Anyway, show that, again, there's nothing conceptually difficult about this, but when you try to write it down, it's gonna push you if you didn't understand all these definitions, if you don't know how to properly manipulate the definitions. Show that okay, maybe I write it like this. Show that this product of this index, the product of this index system of sets and this Cartesian product are in one-to-one correspondence, meaning that there's a bijection between them. And I'm actually telling you the bijection. You just have to check that this is a bijection. What is this? It's a set. What are the elements of this set? Functions. Functions satisfying a certain property. Here's what I do. I define a new function. When I define functions, this is why I said, okay, I said forget everything. I'm going to rephrase that. Forget most of the things you learned in high school, okay? You still need to remember some basic stuff because I don't want to re-explain how we define functions and so on. Anyway, this is that set. The elements of this set are functions, special functions. What I do is I take a function, which is my input. I send it to an ordered pair, this ordered pair, g of 0, g of 1. Prove that this is a bijection. What this shows you is that the notion we introduced actually generalizes the Cartesian product. The usual Cartesian product is a very special case of this notion, okay? Now, this is exercise number 1. Exercise number 2. This is cooler. Okay. Let X be any set. Now, the first part of the exercise, I actually did it over here. Show that the map, the function from, now, I changed my notation, so I need to explain this notation. What this means is, maybe I should do it over here. People sometimes write the following for this. Product as my indices change in the index set I, and over here I'm supposed to write the ith set, f of I. So over there I have the following. I'm taking a product of an index system of sets. My index set is X. The ith set in my index set is fixed. It's the same set all the time, 2. Just like over here. So this is a certain product. Show that the function given by G goes to That's good. In each exercise, I'm just going to introduce different notations. This is what people write in practice when they define functions. G maps to the following set is a bijection. Show that this is a bijection. And you can notice that that set, if you just notice this equality, if you just remember why that was true, you see that this set is the same as set of all functions from x to 2. So what this exercise tells you is that there is a bijection between the set of all functions from x to 2 and the power set of x. Okay? There's a natural bijection. Why is this useful? Like, why am I doing this? You may think that, like, I'm just introducing some abstract nonsense. Pick up some descriptive set theory book or like some topology book. You'll see that they'll talk about a topology defined on the power set of a set. How do they define a topology on the power set? There's a natural topology over here. We can transfer it to over here using this bijection. This is like, these are very common objects used in practice, okay? And I'm introducing this because this is one of the, not the aim of the course, but one of the aims of the course, okay? To show you how certain objects used in practice are defined set theoretically. Well, over here I'm actually not doing that exactly, but whatever. It's the power set.
Power set of that 2, right?
Power set of x.
Is 0, 1, right?
No, power set of x.
No. This P2.
This one.
Pi 2, yes.
Oh, I'm taking the product of the index system, where my index set is x. The ith set in the index set is 2. So basically, I'm taking a product, but I'm taking the product same set over and over again. Think of this as I'm taking the Cartesian product of x copies of the set 2. Okay? Now, we can go back to the question of whether this is empty or not. Again, this exists, but so does the empty set. So why is this not the empty set? Why is this not empty? If it is, maybe it's not. Sorry, maybe it is. Maybe it's not. We don't know it at the moment. It turns out that using the axioms I've introduced so far, indeed you can also have 3 more axioms: replacement, foundation, infinity. I can give you those axioms. I can ask you, like, prove that this is non-empty all the time. You won't be able to do it. It is a theorem that you won't be able to do it. Because, in technical terms, whether this is non-empty or not for arbitrary systems, that's independent of all the axioms except one axiom called the axiom of choice. Okay? So if you disregard the axiom of choice, which I'm going to write down on the board in a second, you cannot prove that this is non-empty for an arbitrary index system of sets. You can prove that this is non-empty for special cases. Okay? Like for that case. You can always prove that this is non-empty for every x. What I'm telling you is, like, what I'm asking is this non-empty for all possible index sets? You cannot prove this without a special axiom called the axiom of choice. And the axiom of choice literally tells you that this is non-empty. Okay? Axiom number what? 7? Okay. This is in the section in our notes, to choose or not to choose. Apparently, I was a bit Shakespearean while writing this. For all sets I and for all indexed systems for all sets ij and for all indexed. No. I need one more thing. Okay, for all sets I, for all sets j, such that no, I don't need that actually. Never mind. I'll just copy this statement so that it will be a shortcut. I can write down the same statement in many different ways, countably many different ways. That's a lie, but only countably many different ways. But I had something in mind, but then I decided to copy what's in the notes. For all indexed system of sets I such that blah 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 the product is non-empty. Now if I don't write anything over there in that space, this is false, because as you can see I can always make this set empty. How can I make this empty? How can I guarantee that this is empty? In order for this to be empty, there should be no set satisfying this. How can you make sure that this is always false? How can you guarantee that this is false? Try this. Okay, forget about this. But how can you guarantee that this is false? If you choose f of I to be the empty set, this is going to be false. Can we pause for a second? So, how can you make this false? If you choose f of I to be the empty set, this is always false. So if any of fi's is empty, you cannot make this statement true. So this is false, so this is empty. So if one of the sets whose product you're taking is empty, then the product is empty, obviously. Okay? You have a question? Well, think about Cartesian products. Is this empty? Why? Because you cannot choose anything from this. What I'm saying is, I don't care how many sets you're multiplying. As long as one of them is empty, it's going to be empty. If you choose one of these fi's to be the empty set, you cannot choose something from that set.
Fi'de empty olamıyor.
What?
Fi boş olamıyor.
This one or this one?
Diğeri. Aynen o.
Sure, but empty set is not a member of the empty set. I'm saying member, not a subset. So if one of these fi's is empty, then this product is empty. So I cannot expect this to be non-empty. However, the axiom of choice tells me that if these are all non-empty, then the product is non-empty, okay? Now, axiom of choice has many different forms. This is one of them. I chose this one to present it in class because this is intuitively the most obvious one. You have a collection of non-empty sets. A collection of non-empty sets. You want to take their product, meaning that, okay, you want to do the following. You have a collection of non-empty sets. You want to choose one element from each of these guys. How are you going to do that? What does it mean to choose one element from each of these guys? Well, let's look at this. A function from this index set to this union chooses one element from each element of this index system of sets. So choosing one element from each of these guys is the same as this product being non-empty. In that sense, axiom of choice tells you that you can choose one element from each set in a collection of non-empty sets, okay? If you have a collection of non-empty sets, you can just choose one element from each of them. Now, how is this used in practice? Let's think of a nice example. Okay, here's an example. Let's say that you do a proof in calculus. You showed that for each natural number, you like have a subset of real numbers, and you show that this is non-empty, okay? And then you do things like this. Then for each I in n, let ai be an element of this set. What you do is, this comes up a lot in proofs, like you show that for each natural number, some set is non-empty, then you want to choose one element from each of those. How are you going to do that? When you do that, you actually use axiom of choice. What you do when you do writing this is the same as doing the following. These guys are non-empty. I can take their product. If their product is non-empty, then there is a function satisfying blah blah. That function exactly does what you want it to do. It chooses one element from each set. Okay, so this is you actually use this a lot in practice without noticing it. And I'm just going over this so that you actually notice it when you use it. Whenever you make infinitely many choices simultaneously, you use axiom of choice. Now, we don't know what the word finite means at the moment. However, if I knew what the word finite meant, I could prove this when I is finite. If you just take the statement, instead of saying for all sets, say for all finite sets I, blah, blah, blah. You can prove that sentence without this axiom, with other axioms. That's called finite axiom of choice. Like, if you just restrict your attention to index sets which are finite, then you can prove this with the other axioms. It's done by induction. We'll see that. However, when the set is infinite, which corresponds intuitively the case where you make infinitely many choices at the same time, infinitely many choices simultaneously, you need to use axiom of choice. You can't do that without this, okay? Now, I had a lemma which is actually equivalent to axiom of choice. It's another form of axiom of choice that says the following. If you have a set whose elements are non-empty sets, then there's a function from that set to the union of that set such that f of m is in M for all blah, 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 blah. That one we're going to prove next time because I don't want to just rush that into 2 minutes. Okay? So study well. As you can see, you started seeing some weird stuff like objects being members of numbers and so on. That should be a sign that something terrible might happen if you don't study, okay? So study well. I'll see you on Tuesday. We do not change the lecture hour on Tuesday because there was no consensus, okay? I'll see you.